Hi all, this is Dr. David Branham. Welcome to the video. This video is over chapter 7 on experimental designs. It is a two-part video where this is part 1. Part 2 will be in a separate video in your assignment. This is going to be pretty comprehensive, so it should help you well with the test. So let's go ahead and get started with the share screen. If I can scroll down here, there we go. Okay, as I said, chapter 7 covers experimental research. We're going to start out with some details about experimental research. First, experimental research design is said to be the gold standard of research designs. And the reason why is because it has, in reality, it has the most internal validity of any research design. It's one of the most rigorous of all research designs. In this design, one or more independent variables are manipulated by the researchers, and these are treatments that are manipulated. And what we do is we can see with this manipulation what the impact is on the dependent variable when we do the manipulation. So in order to make it where we can attribute cause of the by the dependent variable attribute cause of the independent variable onto the dependent variable, we have to have random assignment in our experimental design. That means that once you get your groups together, you randomly assign each person to either a control group or to an experimental group or a treatment group. And your chances of being in either one of those groups in a 2x2 design is 50-50. Everyone has a 50-50 chance to be in each group. There is no self-selection to get in a group. There is no selection by a researcher to get you in a group. Everybody has to have equal chance in these designs. And once you do that and you have two groups that are randomly assigned, then you can assume that those assigned groups are equal. And then any changes that occur in the treatment group that don't occur in the control group can be attributed to the independent variable or the treatment. The results of the treatments on the outcomes of the dependent variable are observed after the random assignment and the treatment. And the unique strength of experimental research is, as I said, is the internal validity that it has. It has causality. We can attribute the cause of the change in the dependent variable on the independent variable that is manipulated. And so due to its ability to link cause with effect, the treatment manipulation with treatment manipulation, while controlling for all the other possible effects by being able to assume equal groups with random assignment, then this is the gold standard of experimental research. Let's see. Experimental research is best suited for explanatory research. Now, if you remember, we previously went over the 3 types of research. There were explanatory research, exploratory research, and descriptive research. Experimental design is best suited for that explanatory research. It's the research that most academics do, and it's the research that's the most complex, because the goal in explanatory research is to examine cause and effect. That's what experimental design is designed to do. It also works well for research that involves a relatively limited and well-defined set of independent variables that can either be manipulated or controlled. If you have a small group, you can still do experimental design. If you don't want to have an entire population in your group, if it just makes it easier to, for instance, have a sample of university students, you can do experimental design with that sample, and you can attribute causation to the independent variable because you'll have 2 equal groups in that sample. Experimental research can be conducted in laboratory or field settings, but field settings are less desirable and less prominent in experimental design because you have to be able to manipulate that independent variable. And since you have to manipulate that independent variable, it's hard sometimes to find an independent variable that you can manipulate in a field setting. It's much easier to do it in a lab. Laboratory experiments tend to be high in internal validity. These experimental designs I mean, they have the cause and effect. I mean, they have the true ability to attribute cause and effect. That internal validity is there, but it comes at a cost of having very low external validity or generalizability to the population in the real world. The reason why is because laboratory settings, especially like in university settings, where I had the example of using university students, people act differently in universities than they do in the rest of the world. There's a culture in universities that people tend to respect. And so they act differently and respond differently in university settings. So attributing something that happens in an experimental design in a university setting to the real world becomes problematic. It's harder to do. Now, it may be the case, but it's often true that we can't really generalize very well from that controlled laboratory setting to the real world because people just tend to act differently. Field experiences are high in both internal and external validity. If you can do experimental design in a field setting, then you have the ability to have both internal and external validity, at least a lot better than you would have in a laboratory setting. But such experiments are rare, as I said, because of the difficulties of getting treatments that you can actually manipulate in a field setting. Experimental research can be grouped into two broad categories. One is true experimental designs, and two is quasi-experimental designs. Both designs require treatment and manipulation, while true experiments also require random assignment. Quasi-experimental designs do not have random assignment. And this makes quasi-experimental designs far inferior to true experimental designs when it comes to internal validity. Random assignment is a process of randomly assigning subjects to an experimental group and a control group. So, for instance, if you had 100 subjects, you want 50 in each group. You want a control group with 50, an experimental group or a treatment group with 50. You would have to find a way to get each person a 50-50 chance of being in each group. And then you assign, by chance, each person to the group before you get started. Those two groups should be assumed or can be assumed to be equal after that random assignment, because there was no bias in the selection process. Non-experimental research includes all types of research that do not employ treatment manipulation or random assignment. These are like survey research, observational research, case studies, where people are just sitting there watching, looking at the environment and coding things. Correlational studies, where they find associations, and these associations, it's impossible for you to find causality in those associations. So, but it does not mean that you want to throw out that research. You want to go ahead and know what those associations are. So non-experimental research doesn't have random assignment, and it doesn't have treatment manipulation, where the independent variable can be manipulated. Now, treatment and control groups in experimental design. Treatment and control groups in experimental research, some subjects are administered one or more experimental stimulus called the treatment, and the other subjects are not given a stimulus. That's the control group. Okay, I think I've went over that before, but I just want to make it clear. So you have two equal groups. In my previous example on the previous slide was 50 in one group, 50 in the other. You give the treatment to the treatment group with 50 people in it, okay? In a properly designed experimental design where members of each group are randomly assigned, you can contribute any difference in the dependent variable to the treatment group. So if you give somebody a pill, let's say we're having a design where you're trying to help a person's health, so you get your group, and one group gets the pill, the other group doesn't get the pill. If that treatment who gets the pill, if that group who gets the pill, if they improve in their health and the other group that doesn't get the pill does not improve in their health, then you can attribute the cause of that improvement to the pill itself. Multiple levels of experimental stimulus may be administered. So you may actually have 3 or 4 groups. For instance, you may give one group a pill, you might give one treatment group 2 pills, and then you'll have a control group who get no pills. And then you can see what the differences are there. But you need to have the random assignment, and you need to have the treatment, the independent variable, which is the treatment. You need to be able to manipulate that. And you do that by saying, okay, you get a pill, you get 2 pills, you don't get any pills. That's the manipulation I'm talking about in that example. So, threats to internal validity in experimental designs. As I said, internal validity in experimental design is better than any other research design. But it doesn't mean that experimental designs are completely shielded from internal validity problems. Although experimental designs are considered more rigorous than other research methods in terms of internal validity, they are not immune to internal validity threats. Some of these threats to internal validity are described below here in this slide. One is the history threat. History is when the extraneous variables from or historical events actually make a change in the dependent variable rather than the treatment itself. So when you split your groups of the 2 groups, you have a control group and you have a treatment group. They're both perfectly equal, but as time goes by, history occurs, and this may cause changes to those people in the group. And those changes may not be because of the independent variable. It may be because of something going on. Now, the good thing is that if you have these 2 groups, the history threat usually affects both of them equally. So there's less problems with internal validity with experimental designs when it comes to history threat. But it still can be the case that the changes are occurring due to history and not due to the manipulated independent variable. Maturation threat is another one. It just refers to the possibility that events or the effects of aging can actually change the dependent variable. This is especially true in children. As children get older, they get much more intelligent, much more mature in quick order. Now, it may not seem like that, to the parents, but it's true. When you're a child and you're growing up, you mature very quickly. So that may be the impact on the dependent variable instead of the treatment itself. So that's a possibility. But as I said before, this usually affects both groups equally. Remember, you have random assignment, so you can assume they're going to be equal, and you can probably assume that maturation effects will be equal across groups as well. Then there's the mortality threat, which refers to the possibility that subjects may drop out of the study at different rates between the treatment and the control groups due to a systematic reason, such as that, the students who don't do well in the pretest may just drop out. And so that's a problem that isn't easily covered in experimental design, because when you have dropouts, then you can't measure the dependent variable effect on your entire population inside your sample, the entire population in your group. And when people drop out, then you may incur a bias in that situation. When that happens, then mortality can be a really disturbing threat for experimental design, and internal validity problems may occur. So by far, the biggest problem with internal validity on experimental designs is the mortality threat. So 2-group experimental designs, the simplest true experimental design is the 2-group design involving one treatment group and one control group. And these are suited for testing the effects of one independent variable that can be manipulated. And all you're going to do is manipulate it once, right? For instance, the pill, you're going to give one group the pill and one group not the pill. So you have 2 basic designs. One is the pre-test, post-test control group design, and the other is the post-test only control group design. Now, these 2 designs are here on this slide. And the first one, the pre-test, post-test control group design, is in that green box on the left, and then you have the post-test only control group design, which is in the green box on the right. So these boxes have R's, O's, and X's in them and have numbers in them. So you should understand these abbreviations. So R represents the randomly assigned subjects in the group. So R means that everybody in that group was randomly assigned in that group. And that means you're going to have two R's in these because you're going to have two groups, and each member of those two groups are randomly assigned. X is the treatment. So for instance, on my previous example, the pill, whether or not you get the pill is the treatment. Okay. So on that first design, the post-test, pre-test, post-test, you see the top group is the treatment group. They're going to get X if you go across. That second group is the control group. They're not going to get X. So you can see where the treatment manipulation is in this design. When you go over to the right to the post-test only control group design, you see the same thing. The treatment group gets the X. The control group doesn't get the X. Okay. And then you have O, which represents the pre-test or post-test observations of the dependent variable with different subscripts there. The subscripts are the little numbers to distinguish between the pre-test and post-test observations of the treatment and control group. So I think these are pretty simple to see if you look at it. So let's look at that first one, the pre-test, post-test control group design. You'll see that they have random assignment of two groups. Right away, you have two groups. So we have group one, the treatment group. Group two is control group. Then you have O1 for the treatment group. And O1 means that's the measure of the dependent variable right there as soon as you make the random assignment. You do a measure of the dependent variable. Below in the control group, which is O3, then you have a measure of the dependent variable for that group. So theoretically, these two measurements should be equal. If you do this pre-test, post-test control group design, the value of this pre-test is to see if you really are equal in your dependent variable, with these two groups. In almost every case, you should be pretty close to equal on O1 and O3 because the two groups are randomly assigned. There's no reason for them to be any difference in them. So O1 and O3 should probably be equal. Then you give the treatment to the treatment group. You give no treatment to the control group. If it's a pill, a lot of times you'll use a placebo. I'll talk about that in a second. Where you have a pill that looks the same, so they don't know whether they're actually getting the real pill or not, and that helps to alleviate the effects of knowing you're getting the drug. So a lot of times, especially when it comes to pills, you get a placebo in the control group. Then O2 and O4 are the measures of the dependent variable after the treatment. Now, so O3, if everything is steady and nothing changes, O3 and O4 will be the same. And then O1 and O2 will be different if in your hypothesis because they're getting the treatment. So for instance, if it's a blood pressure, if blood pressure is your dependent variable and you have a pill X that you get for that, then that pill X should account for the change in blood pressure from O1 to O2. And then O3 to O4, you're not going to see any change in blood pressure because that group actually didn't get any treatment at all. So what you want to look at to find your effect, which is the E below, the effect equals O2 minus O1, which means there's the change in the treatment group, minus O4 minus O3, which is the change in the control group. So this helps you with history effects, maturation effects, that type of thing that happens as a result of things outside the laboratory. So you can see if O3 and O4 change, then you're getting some effects that aren't attributed to the treatment. And so you're controlling for that possibility. So the effect E of the experimental treatment in the pre-test, post-test design is measured as the difference in the post-test and pre-test scores between the treatment group and the control group. So if the treatment group blood pressure went down 10 points, the control group blood pressure went down 5 points, then you will find that the pill can be attributed with 5 points lower in blood pressure. And the control group might have went down in blood pressure because they think, for instance, you might psychologically think you're getting a blood pressure pill and your blood pressure goes down. That could be a possibility. So you could do that with both groups and you get to see that. That effect, that O3 to O4 effect, can be found in this design. You can't find it in the post-test only design, but that's okay, because in reality, both groups are assumed to be equal anyway. So in the post-test only control group design, you have random assignment, you have a treatment for the treatment group, no treatment for the control group, and then you compare O2 and O1. And that difference between O2 and O1 and O2 is the effect of the treatment on the dependent variable. So if it's a blood pressure pill and you give that blood pressure pill to the randomly assigned treatment group, you don't give it to the randomly assigned control group, and you look and see, okay, O1 blood pressure is 5 points lower than O2 blood pressure, you can attribute that to the pill. So that's the difference between the two designs. The pre-test, post-test control group design, it only helps you if, one, if you have, after random assignment, you really do have some uneven groups. It may help you in that situation to continue to have an internal validity in your design if you just have bad luck with your random assignment. If you have a big enough sample, it's almost never an issue. So that's the only thing that it really gives you. And it tells you possibly about history and maturation effects. If you want to measure those, you can see that in O3 and O4, that difference between O3 and O4, or just, the fact that you're getting in treatment, that may affect you. So that's where you see the advantage of the pre-test, post-test control group design. But when it comes to actually your hypothesis, there's not really a good reason for O1 and O3. You don't really need that in your hypothesis test because you can assume your two groups are equal if you randomly assign them. So an example, I'm going to give you an example of the pre-test, post-test control group design. Let's say we have 60 people gathered for the test. 30 people are randomly assigned into each group. The group getting the weight loss pill, X, which is the treatment. You can see in the green box down there. And then the other group getting a fake pill, which is the O3 and the empty space between O3 and O4, which is the control group. So the fake pill is called a placebo. You should know what that is. A placebo is just something that looks like the treatment so that you won't have a treatment effect where one group gets a treatment effect just from getting the pill and the other group doesn't. So getting the pill, if everybody gets a pill, they don't know whether they're actually getting the real pill or not. The treatment is then administered to the treatment group. The placebo is given to the control group. And then after the treatment, each group member is weighed again. And then the average weight of the group in O2 and the control group O4 is taken. So at first, at O1 and O3, they weigh everybody. In my example up here, the average weight of the control group is 146 in O1. The average weight of the treatment group in O3 is 148. They take the pill, and then after the pill is taken, they come in at an exact time, same time, and everybody weighs. In this example, the post-treatment group weighs 141 on average. The average weight of the post-treatment control group is 144. So the effect of the experimental treatment in the pre-test, post-test design is measured as the difference between the post-test and pre-test scores between the treatment and control groups. So the equation is E equals O2 minus O1 minus O4 minus O3. And then you use that. So the E equals 148 minus 141 because the treatment group lost 7 pounds minus 146 minus 144 because the control group lost 2 pounds, maybe just because they think they're going to lose weight from the pill. So 5 pounds can be attributed to the treatment group. So that treatment can be said to help each individual lose about 5 pounds. A t-test or ANOVA can be calculated to see if the difference is really statistically significant. I'll cover that in part 2 of this video, and that will be covered on your statistics class in great detail. So that is not a big importance in this class, although we'll go over it some. It's going to be much more important in your statistics class. Then the second example is the post-test only group design, which is a little bit easier because you just don't have to weigh everybody before, right? So 60 people are gathered for the test, and then 30 people are randomly assigned into each group. The group getting the weight loss pill, X, is the treatment group. The group getting the fake pill, the blank spot between R and O2, that's the control group. The treatment is administered to the treatment group. The placebo is administered to the control group. Notice that there's no weight in before. There's no O1 or O3. Random assignment allows you to actually assume that this pre-weight average is equal for both groups. Now, sometimes it isn't, it's off a little bit, but it's okay to assume, as long as you do random assignment and you're not doing self-selection, it's okay to assume they're equal. After the treatment, each member of each group is weighed, and the average weight of the treatment group and the control group is taken. In this example, the weight of the post-treatment group is 141. The average weight of the post-test control group, the treatment group is 141. The post-test control group is 144. So the effect of the experimental design is E equals O1 minus O2. And so E equals 141 minus 144, which means that 3 pounds can be accredited to the weight loss pill for each member of the treatment group. As with the previous example, you can use a t-test or ANOVA to find out if it's statistically significant. We'll go over that a little bit later in part 2, as I said. But that is the design. And both the designs are very viable. Both designs have a lot of internal validity. And you can attribute causation because, 1, you can manipulate the treatment group, and 2, because you have random assignments to the groups. So, as I said, even though validity concerns are a lot less in experimental design, they're still there. Several threats to internal validity, as I'll remind you. Maturation is one of them. History is another that isn't listed here. But the other groups like testing and regression, these problems are not a big issue with experimental design because they're expected to influence the treatment and the control group in a similar random manner. So the threats are really not as big a problem in experimental design. That's a reason why it has so much more internal validity. If something going on is having an impact on the treatment group, then the same thing is probably going on with the control group. Selection threat is control via a random assignment. So you're not going to have a selection threat. You don't get to go in the group that you want to. No one gets to choose which group. Even the researcher absolutely cannot place people in the experimental group as opposed to the control group. And mortality is a problem especially if there's a differential dropout rate between the two groups. If one group is getting a lot of dropouts, another group isn't, then mortality is really a problem. And that's by far the biggest problem in experimental design is mortality threat. Then there's factorial designs, and these are more complex experimental designs. Factorial designs are experimental design models with 2 or more manipulated independent variables. So you won't just have a pill, you'll have something else. So these independent variables are called factors, and each subdivision of a factor is called a level. So the most basic factorial design, just think of the most basic. No, you can get bigger and bigger factorial designs, and they can grow exponentially. But you also have a problem in this, and remember, you have to have, every time you add a level, you have to double your groups. So that is a problem. So the most basic factorial design is a 2x2 factorial design, which consists of 2 treatments, each with 2 levels, such as a high-low or a present-absent. So factorial design example here. The book's example is here, and it compares the learning outcomes of the two different types of instructional techniques. And so it has in-class versus online instruction. So that's the first factor, in-class versus online. And then you want to examine whether these factors vary in as far as length of instruction, 1.5 hours a week compared to 3 hours per week. This is pretty close to a lot of UHD classes. There's a lot of classes like this, hybrid versus fully face-to-face and so forth. In this case, you have two factors. You got the instructional type, right? In class versus online, and you got the instructional time, 1.5 versus 3 hours a week. You have two levels. You have in class and online for instructional type, and 1.5 and 3 hours for instructional time. Okay, so the figure 7.4 in your book, this figure's in your book, and it shows that 2x2 factorial design. And so in this case, R equals random assignment. So because it's 2x2, because you have two variables with two values for your independent variables, you actually have 4 groups. So you have 4 R's there. That means you randomly assign your subjects into 4 groups. Well, think about this. If you want, if you like to have a nice big group, so let's say if you like to have 100 in each group, that means you're going to have to get 400. Just adding the second variable doubles the number of people that you need to have in order to have that number. And you need that high number in each group in order to find statistical significance later on, because the more you have, the better chance you have of finding statistical significance if the effect is really there. If the effect isn't really there, having a high number isn't going to matter on your statistical significance. But if you see a big group difference between group 1 and group 2, you want to be able to find that. And the only way to find that is if you put 5 people in each group, you're not going to find that. It's not, statistical significance will, the T-score will say this is just by chance, because anything can happen with only 5 in one group. You need bigger groups. So remember, in factorial designs, adding that second variable means you're going to do a lot more work. So R means, if you go over there in that design notation over on the right of the figure, R means random assignment into the group. X is the treatment. Now you notice there's 4 treatments here. Yes, there's the first treatment and the second treatment. The first treatment, so you see X11. The first treatment is 1 if you're doing in class, 2 if you're doing online. So the first X says 1, 1. That means 1, they're doing it in class, and all the 2s, the first 2 on each X means they're doing it online. The second one, the 1 means you're doing it in 1.5 hours. The 2 means you're doing it in 3 hours. So the X on the first row, 1, 1, that means you're doing in class for 1.5 hours a week. 1, 2 means you're doing it in class for 3 hours a week. 2, 1 means you're doing it online for 1.5 hours a week. And 2 means you're doing it online for 3 hours a week. You have 4 groups. And then you'd find out, once you do this design, you see what your changes are in your independent variable, your dependent variable for each of these groups. And you do a statistical test to find out if it's statistically significant. So the factorial design is kind of cool because you can use more than one independent variable, but it also comes at a lot of cost. So quasi-experimental designs are almost identical to true experimental designs, but there's one lacking ingredient, and that's random assignment. And what happens is you do these a lot in the field experiments because you can't do random assignment. For instance, one entire class section or one organization is used as a treatment group. So you might use one class as a control group, one class as a treatment group. In most cases, you do a pre-test, post-test, because you don't know for sure that they're equal because they're not randomly assigned. So that pre-test, post-test design works a lot better with quasi-experimental designs because, for instance, if you're doing the weight loss pill, you may have a class where they're averaging 155 and another class that's averaging 135. So you need to know that beforehand to see what that weight change difference is. because those two classes are not going to be equal because they're not randomly assigned. So one entire class section may be used as a control group, another one as a treatment group, while the same class, this one class is used, you can actually do designs with more than one independent variable if you want to do this, and just use classes as your groups. But they aren't randomly assigned, so make sure you should do the pretest when you do these. And this lack of random assignment potentially results in groups being non-equivalent. We know they're going to be non-equivalent. So if you get, for instance, if you get a 155 weight average in one class and 135 in the other, if you have a weight loss pill and you're giving it to the 135 class, there's a lot less weight to gain in that situation than from the 155 class. So you'll have to take that into account as well. If there's extreme differences between your control group and your treatment group in the pretest, you should take that into account in deciding, how to actually interpret your findings. Quasi-experimental designs are therefore inferior to true experimental designs in internal validity due to the presence of a variety of selection-related threats. So you have maturation threat is a problem, history threat is a problem, regression threat, the treatment and the control groups regressing towards the mean. I think I had regression threat on the previous one, but regression is the tendency to regress to the mean. So if you have a group that does extremely well on the test, where say they make a 97 average on the test, it's going to be very difficult for them to raise that average. In most cases, they're going to go down to what, let's say the average was 85. A group that's averaging 97 will probably go closer to 85, while a group that's averaging 65 will probably go closer to 85 too. And that's a regression threat, where the effect is just, okay, we tend to go towards the mean in that situation, and it's not attributed to any treatment. Instrumentation threat, the treatment and control groups will respond differently to a measurement. That's a problem in quasi-experimental designs. And testing, the treatment and control groups responding differently to a pretest. For instance, if you have a pretest to a group and they don't do very well in the pretest, they may not want to go to the post-test, or they may not want to stay in the experiment. And we'll find out from chapter 9 that you don't have to stay in the experiment if you don't want to. People can drop out whenever they want to. And so that becomes a problem in your groups being biased because of the mortality threat that occurs. Giving these selection threats is generally preferable to avoid quasi-experimental designs if true experimental design is a possibility. So we do know that, but it doesn't mean that quasi-experimental designs shouldn't be done. In most cases, when they are done, it's because a true experimental design is not an option. So that doesn't mean we throw out the baby with the bathwater. Go ahead and do the quasi-experimental design, explain what you did, and let people make their own conclusions from it. The experimental design quasi-experimental design example. This is a single group pre-test quasi-experimental design with two outcome measures. It's pretty simple, okay? One measure is theoretically expected to be influenced by treatment. The other measure isn't. And this is the book example. For instance, you're designing a new calculus curriculum for high school students. And this curriculum is likely to influence the students' post-test calculus scores, but not the algebra scores. So you would think that people would improve in calculus at the same rate as they improve in algebra. So one possibility is to use the algebra scores as something of a control group. So since the algebra is not getting the new curriculum, calculus is getting the new curriculum. What you do is you have that pre-test, O1 and O2, to measure where all the students are. You implement that new calculus curriculum up there on O1, which is the treatment group. The calculus curriculum is the X in that situation. Then you measure the new calculus score and the new algebra score. And then you see if there's a difference between O1 and O2. So if O1 is moves a lot and O2 doesn't, then you could probably attribute it to the calculus curriculum. So in the book example, you are designing a new calculus curriculum. The curriculum is likely to influence the students' post-calculus scores, but not the algebra scores. However, the post-test algebra scores may still vary due to extraneous variables like history and maturation. Algebra scores will go up at their normal rate because there's no treatment to them, so they should go up as they usually do. What we're looking for is see if the calculus scores go up as they usually do with the new curriculum or even better. And if they're even better than they usually are, then we can attribute that to the calculus curriculum. The design notation in 7.5 indicates that there's a single group, and that's N. So each group is a single group. One's the calculus scores, one's the algebra scores, followed by a pretest, O1 and O2, and then a post-test, O1 and O2. So this design is weak in internal validity because you have all these internal threats, because it doesn't use that separate control group that's randomly assigned. It's impossible in this situation to do it. But because you can still use this as quasi-experimental design and maybe draw some conclusions that the curriculum is doing well, then it's something you probably should implement if it's your best option. Okay, that ends part 1 of the video on chapter 7. After this, I would go on to part 2, where we're going to start looking more at the calculation of the dependent variable changes in these models. So thank you for watching this video and have a good day.